So image filtration. Uh, why should we use image filtration? We are measuring our AFM images with a microscope. Microscope is a device, electronic device, and every time we talk about electronic measurements, we remember that our result contains both signal and noise. So the set of filtration methods are dedicated uh, to remove noise and to leave our signal, our information about our objects. So first set of filtration methods is a spatial set of spatial methods when we apply filters in a normal space. How do we do this? Normally we convolve, we have the set of filters, which is marked on this slide as H, and we convolve our original image with this filter and get the filtered result. So, and I would like to advise in your following work to you. We have a nice module which is called Filter Generator, when you can choose different kinds of filters and to play with them, to design your own filters, to play with parameters, and to optimize the result. It can be found in section editing and is named Filter Generator. So first of all, a few words about low-pass filtration. So here you can see the image, which has nice features, but also you can see high frequency noise in it. And filtration, we can want to use filtration to eliminate this high frequency noise. So if we apply smoothing filter, which has kernel matrix looking as this. What does this matrix mean? This matrix means that for the central point, we convolve the surrounding points, and actually in this case the central point will be the average from the surrounding points. That means that if we have some high frequency noise, this noise will be averaged. I just want to notice that in our software we use normalized filters, because if you apply this filter directly with this once, you will get the wrong result. So for this 3x3 kernel, each weight is normalized by 1/9. So, and from the right side, you can see that this high frequency noise has gone. But what will happen if we apply filter with the bigger kernel, like 5x5? We'll see that image became even more smoother. But we have lost some details already. That means that the next idea I just want to highlight is that when you use some tool, please don't use it too much. Like in this case, don't overfilter your image. Another example of kernel spatial image filter application is high pass filtration. How can this be used? So from the left side here, you can see the image which has some big objects, but we cannot see details at all. And if we use another filter, which is actually the differential filter. That means that for the central point, we are getting the gradient in this direction, in a horizontal direction. And as a result, we see actually the x derivative of the image from the left. And we can see the features which were hidden from the left side. So this is an example how the high-pass filtration can help us. So here is the list of the filters we have by default. It's like smoothing filters, uniform Gaussian, differential, and high-pass filters. And also you can design your own filter with kernels from 3 by 3 to 7 by 7, and to play with the results and maybe to invent some new kind of filter. Another way of filtration is medium filtration. Comparing to these kernel filters I mentioned previously, the medium filtration is nonlinear filtration, and it cannot be described as a convolution of of two matrices. So how does it work? Here is the example how it works in the case of single dimension. Like we have from the top they have the input array, which has the central point which we are filtering, and it has some surrounding. So median filter uh, puts these points uh, in row by increment of the value, and leaves and writes to our process point. It writes the value which is the mean from this point. That means that this filter, if we have some spikes on the image, this filter will eliminate the spikes. And as an example, there is an image, we can guess that there is something, but due to some multiple spikes, positive and negative, we don't see really the details. We don't see the information. We see the noise. And if we apply median filter, that's another story. We can see all the details and spikes are eliminated. But at the same time, if we take too big kernel of this, too big matrix of this median filter, meaning that we'll use not 3 by 3 like in previous case, like here, but for example 5 by 5, our details start to disappear. So together with noise, we start to distort the signal. So once again, when you use some tools, don't use them too much. Another way of filtration is filtration in frequencies domain. So for this, we are using the Fourier filtration. From the left side, well-known equations for Fourier the transfer forward transform and inverse transform for infinite function. But as we are dealing with discrete numbers, we use the discrete Fourier transform. And what does it mean? What does the Fourier transform means? Fourier transform transforms our image from normal space to frequency domain. And this is an example how the image of from the left side we have see the normal image, from the right side we see the image in frequency domain. And what do these spikes mean? These spikes mean that we have some periodicity in this or that direction. That's the first point. And the second point, how to read this Fourier image. The smallest frequencies are laying in the middle, and the more far frequency we get, the more far the frequency the spike is from the center of the image, the higher is the frequency. So how to run the frequency filtration in frequency domain? So there is another image which also has some high frequency noise, and if we look at the frequency image of the frequency Fourier transform image of this scan, we can see that well, in the middle we have some big number of frequencies which likely correspond to information in our image. And also we have some, we see that there are some high frequencies which probably correspond to the noise. And if we use the band pass filtering, meaning that we delete everything which is outside of the chosen band, everything which has higher frequency or smaller wavelength than than the chosen threshold, you'll see that this high frequency noise has gone, and from the right bottom, you can see the difference, and you'll see that really high frequency noises have gone. But again, if we use this filter too much, meaning that we decrease the band of the filter too much, we'll start to see that the image has lost plenty of details, and what we see in difference between the result and the original image, we see that the objects really start to appear in this difference. And this is a good indicator that we have used our filter too much. If you see your objects clearly in the difference image, that means that you over-filtered your image. So just try to avoid this. Another example of filtration, like previously we used band filtration, and here is another example how to use the local filter, because we can choose some specific frequencies and delete only them, not all frequencies which lay higher or lower some threshold. So from the left side you can see the image, which has very specific artifacts, very common artifacts which can meet frequently. These artifacts come from bad vibration isolation of the system, and if you don't have active vibration isolation, and especially somebody is walking loudly in your lab, most likely you see these artifacts like horizontal lines in your images, especially in flat images. So in this example, from the right side we see the spectrum of this image, and we see that there are some frequencies which lay from the top and bottom of the main spectrum. And this means that these frequencies correspond to something which is periodic in a vertical direction. And okay, these lines also have some vertical periodicity. And using choosing the local filter tab and using the rectangular selection tool, we choose these frequencies, and when we apply this filter, deleting these frequencies, we can see that this annoying lines disappeared from our original image, and in the end we start to see them in the difference image. Another example, just to highlight the frequency nature of the Fourier transform. Here is another nice example of the image of lattice spheres, which and the periodicity of the structure can be seen even by eye. And from the right side we see nice clear Fourier transforms of this image, and these spikes, they indicate that there is very strong periodicity in the image. And just what if we would choose some main spikes and delete everything else? We can do this using the ellipsoidal selection tool from the toolbar, and also using local filter tab. And when we apply this transform, we will see that the inverse Fourier transform of this spectrum, this dark spectrum where we left just these main spikes, it gives us only the main periodicity. So we see a nice periodic structure. And the difference between them shows us that periodicity almost disappeared from the main image.